Okay, so thanks for coming to hear me. I'm going to talk about this and some other new things that we've been doing with QuickCheck. But I want to start off by asking everybody a question. Who here really, really loves testing? Okay, that's actually more than I usually get. So for most people, testing, it's not really the thing you look forward to doing in the morning. It's more of a chore that you have to get done. So I want to think a little bit about why that is. Why is testing hard? Well, suppose you're testing some code and you've got, let's say, n features to test. You're going to write maybe 3 or 4 tests per feature, right? That's kind of realistic. And that's okay. That's a linear amount of work. No problem. But we all know that you won't find all of your bugs if you do that, because some bugs only appear when you test 2 features together. It's some kind of feature interaction. So let's suppose you wanted to test for all of those possible bugs. Well, now you'd have to write a quadratic number of test cases. That doesn't sound so good. And actually, you won't find all of your bugs if you do that either, because some bugs only appear when 3 or more features interact. So, are we going to write a cubic number of test cases for all triples of features? This is starting to really sound like a lot of work. And it doesn't even stop there. So this is the problem with testing. You can't test everything. When are you going to stop? What's the answer? Simple. Don't write tests. Generate them. And that is what QuickCheck does. QuickCheck has quite a long history. It dates back to 1999 when Koen Klaassen and I came up with the first version for Haskell. In 2006, now then, Thomas Arts and I founded Qvik to market an Erlang version. And since then, we've added lots and lots of extensions, and we found lots and lots of cool bugs, all with variations on random testing. That's what the dice are for. So I'm going to start off by doing a very simple example of QuickCheck testing. And I want you to think back to your first or second year data structures course. I know it was a long time ago, but nevertheless, I'm just going to use an example from that because it's simple. I'm going to test some code for implementing binary trees, ordered binary trees. So I'm going to represent them in Erlang as either a leaf, that's just an atom, or a node with 2 subtrees. And that's going to be a tuple with a node tag, and then a left subtree, the value in the node, and the right subtree. And here are a couple of functions that I want to provide on my trees. ToList just converts a tree into an ordered list. A leaf is mapped to the empty list. A node you make a list out of by making lists from the subtrees and concatenating them together. And here's the member function. Very straightforward. If you want to test whether something is a member of a leaf, well, it's not. Otherwise, you compare the thing you're looking up with the value in the node, and then if it's less than, you go to the left subtree. If it's equal, well, you found it, and if it's greater, you go to the right. It's very easy. OK, so imagine we're testing these 2 functions. Of course, you could write some test cases. But I don't want to do that. What I'm going to do instead is show you how we test it with QuickCheck. Instead of writing 1 or more test cases, we write a general property. Here's how the property for testing these functions might look. So it's an Erlang function definition. A property of members says, not for any particular test case, but for all test cases with x, that's the value we're going to look up, and t, that's the tree we're going to look in. So for all x and t that are generated by that generator there, and I'm going to use a natural number as test data and a tree, then it must be the case that the equation on the next line holds. So what I'm using here is I'm using the lists member function as a model to predict how the trees member function should behave. And I can do that because, luckily, I have a function to convert a tree to a list. So I'm just going to check that the answer that the tree member function gives me is the same answer as I would get if I convert the tree to a list and then ask whether the element is a member of the list. OK, so I'm actually going to test this in front of you. let me run some tests. And to do that, I'm going to have to change my screen mode. Come on, you so-and-so. OK, good. So here's the Erlang shell. I'll just compile my trees module. Can you see that? Yes. And now I'll call QuickCheck, giving it that property as an argument. So this is what we do with QuickCheck. We define a property as a function, and then we pass it to QuickCheck for testing. And what do you know? A test fails. And when a test fails, what QuickCheck does is it shows us the failing test case. So here, this line is a randomly generated test case that failed. And as you can see, it's fairly long. The next thing QuickCheck does is it tries to shrink the test case to a simpler one so that we have something simple to debug. We see that happening here where it says shrinking. And down here, we have a case we tested with a 1 was a member of this tree. And QuickCheck says false is not equal to true. That is, the tree's member function returned false. The list's one returned true. So those are different, and the test failed. And if I test this several times, let's see, you can see that the random test case that QuickCheck first finds can be quite complicated. But after shrinking it down, we have a very simple one. Actually, they're always the same size. They just have 2 nodes in the tree. So that's good. OK, so how do I fix the bug? Well, I'm going to use the Windows shell for this. You may not have seen this technique before. I don't know if you can even read that. But I'm going to copy treesfixed.erl over trees.erl. OK, did that work? Back to Erlang. Let me recompile my code, and now rerun the tests. And now every one of those dots is a passing test. So we can see lots and lots of random tests are passing. So probably my code works now. Back to the slides. So what have we seen? Well, we've seen that QuickCheck could find failing test cases very easily. And we've also seen the shrinking, which is tremendously important when you're using random testing like this. Random test cases usually are much larger than they need to be to provoke a failure. Usually you get a random test case with a lot of noise in it and just a few key elements that provoke the failure. Random tests contain a lot of noise because that is their purpose. But when you want to debug a failure, you don't want to see it. You want to see a test case that just contains as much as is needed to cause the code to fail. We think of that as the signal. And the shrinking process extracts the signal from the noise. It's critically important. OK, so now you've seen me find and fix a bug. But wait a minute. What was the example that failed? Do you remember? I bet you don't. I certainly don't. So this is one of the downsides of testing in this manner, that you don't have a permanent record of your test cases. So if I wanted to keep that test case and put it into a regression suite, I would have to have thought of that a few minutes ago. And I can't even be 100% sure that I fixed the bug. Maybe I was just lucky the first time when QuickCheck found it. Well, OK, you saw me being lucky in that case repeatedly. But maybe I'm just being unlucky now. How do I know that the test case that failed before is even being generated? So in reality, when we run QuickCheck on real code, we often don't find bugs. Well, at least after the code starts working better, we don't find bugs as quickly as I showed you. Sometimes we run QuickCheck overnight, and it may take hours to find and shrink a failing test case. Well, you don't want to just throw those away. This is where QuickCheck-CI comes in. Now, I wanted to show you a demo of QuickCheck-CI at this point. But you know what? It's a website. And after playing with the network a little bit, I thought, no, this is just unwise. So no demo, but a virtual demo. So bear with me here. Here we are. This is what QuickCheck-CI looks like. You just enter quickcheckci.com into your browser, and you come to this page. And there's a welcome message, which I'm sure nobody reads. But then you can click Register Your Project, which takes you here. This comes to the project registration page with a lot of instructions, which we know nobody reads. But right down at the bottom, there's a place where you can enter. Let's just expand that, zoom in a little bit. There's a place where you can enter a project URL. And these URLs must always be GitHub projects. So if you have a GitHub project and you want to try this out, just go ahead. So I enter the project URL there, and then click on Register Project. And we come here to the QuickCheck-CI page for this project. This project has not yet been built. Fine, please queue a build. How do I do that? Look, there's a button, Queue Build. Press that, and after a moment or two, we come here. So this is what you see when you run tests in QuickCheck-CI. Up at the top here, we have a timeline with a lot of dots in it, and every dot is a build. So that red circle there, that tells us that we've done one build, and it's red because the tests failed. And then below that, we see more detail about which tests failed. And at this level, we see a list of modules. There's only one module in this project. It's so simple. And I can see that tests failed in the module trees. And then we can just drill down into this. Let's click on trees. And we see the properties that I wrote. I actually wrote two properties. I only showed you prop member. Prop ordered says that when you convert a tree to a list, you get an ordered list. So that just checks the invariant on trees. And that one passed. It's green, but prop member failed. Before I look at the failing tests, I want to show you the coverage tool that we've got. You can see on each of these tabs, you can look at modules, properties, or whatever, but also coverage. So let me look at the coverage of the properties for this module. Look, I have 100% test coverage. Isn't that great? And if I click on trees, then we come to the coverage information. So we've built our own coverage tool, which we think is rather nice. I'm sure most of you have used cover that comes together with Erlang. But that does have some limitations, some of which we've addressed here. So one of the nice things here is that instead of needing to look at the left-hand side to see whether you have a 0 executions of a line or a positive number, here coverage is color-coded. So the green code has been covered in the tests. And what's more, how dark the shade of green is lets you see visually which code has been tested a lot and which code has been tested a little. Up at the top there, there's a scroll bar that you can scroll through the file with, and you can see where the heavily tested code is and where the less heavily tested code is. And then if you hover over a line here, then you can see, OK, prop ordered, that's the property I showed you. That was called once to create the property for testing when it was passed to QuickCheck. If I move the mouse down, this ordered predicate, that was called 100 times. And we can even see that in toList, if I scroll down a bit, the first clause was called 1,200 times, and the second clause was used 960 times. So you get very, very detailed information. You can even see that it was called 500 times from the prop ordered test and 435 times from the prop member test. So you can see which property tested each line of code. And you can also see which parts within a line were executed, so that you get very fine-grained information from the tool, which we like. OK, let's go back to the test results. So if I come back here, this shows me the properties, and we see that prop member failed. And if I click on prop member, then we see not one, but a number of failing tests. And now, if you like, you can look through those, and you see on the web page what the test data was, so you can compare and see is there a pattern. But let's go to the first of those tests and fix the problem. OK, so if I open that, now we come to a page that shows the QuickCheck output, just as you saw when I ran the test in the Erlang shell. OK, so now we can see I was looking for the value 1 in this tree containing a -1 and a 1. So I could start looking at my code and trying to debug it. But let me show you a neat trick. Do you see there's a coverage entry for this single test? That'll show me the coverage of just this test case. Let's click on that. Oh, this test case only covered 44% of the code. That's good. I know the bug must be in the covered code. So let's look at the file. Here it is. And scroll down. OK, now remember, this is the coverage of a failed test. So red is good, and green is bad. Which clause in the member function do you think is buggy? Well, obviously this one. I know you probably can't read that. Here's what it says. It says if x is greater than y, x is what we're looking for, y is the value in the node. If x is greater, then look in the left subtree. It should be the right subtree, of course. So that was my bug. OK, so suppose I make this fix, and I go back to the interface, and I queue another build. What happens? Well, we come here. You can see the second build has appeared in a line of dots, but it's still red. The test still failed. Did I make any progress? Let's click down to the properties. Prop member still fails. Oh, but now a bunch of examples have passed. So this is kind of nice. One of the things that can be a bit depressing when you're using QuickCheck is that you run QuickCheck, it finds a bug, you fix it, you run QuickCheck, it says, here's a bug. So you can't see that you made progress. But here we can. All of those test cases that QuickCheck previously found now pass. But the second one still fails. So let's have a look at that one. That's another tree with 2 nodes. I'm going to pull the same trick and look at the coverage. Yeah, 44%. Here's the coverage of the member function. Look, the other clause is wrong. I am nothing if not consistent. So I made the same mistake, well, the opposite mistake here. So I need to replace that by L. And if I do that, then queue another build. This time, the tests turn green. OK, so OK, if we click in, we can see both properties passed, and now all of the test cases passed. Let's just look at the coverage that we've got now that all the tests are passing. Oh dear, it's only 97.5%. I had 100% coverage before. What's gone wrong? We'll have a look at it. Oh, look at the top. There's one piece of uncovered code, that little red bar. Where is it? It's here, inside a shrink. I'm not going to explain this in detail, but shrink lets us define code that is only used to shrink failing tests. So if you don't have any failing tests, you're not going to use the code. That's why that's not covered. OK, so now we've seen QuickCheck-CI in action, at least virtually. What does it do for us? Well, it builds a regression test suite automatically. That's nice for 2 reasons. It lets us see exactly which tests we've managed to fix, so we can see what progress we're making. And it also, if a test is hard to find, so it's rarely generated, then it gets saved and it gets rerun in every future build, unless you disable it. You can disable tests if you want, but by default, we now save rare tests. And so errors that were hard to find, we keep testing for. And the other nice thing is that you get this coverage information in a lot of depth. you can see at a glance what you have tested. Because of this shading that we use, you can also see what you tested heavily and what you tested lightly. And since a part of using QuickCheck is tuning your test case distribution so that you test all your code well, then that's very useful information for doing that tuning. And finally, as I showed you, coverage actually can help you find bugs. It's not just for producing a percentage to tell your manager. OK, so how am I doing for time? All right. I also want to show you some more interesting testing, more interesting example. State machine testing, which is fundamental to a lot of the real testing that we do with QuickCheck. But I'm again going to use a very simple example, the process registry. So I'm going to test two operations, the register operation and the unregister operation. But my test cases are also going to need to contain calls to a spawn function so that I have some PIDs to register. And quite often, I need to add some operations to my test cases just so that I have test data to test the ones I really want to test. So this spawn function is something I've written myself. It just spawns a zombie process that can be registered and unregistered. OK, so what's different between testing the process registry and testing that little trees module? The difference is that these functions change the state of the registry, and I have to take that into account in my tests. Now, you may also be wondering, is the process registry buggy? Well, of course not. I'm not looking for bugs in the process registry. If I found one, oh, that would be brilliant, but it's been around for so long that I'm sure it works perfectly fine. What I'm going to do is I'm going to reverse engineer the preconditions. So register and unregister, they raise exceptions sometimes. There's a way you're supposed to call them. And I'm going to figure out what that way is. So I'm using QuickCheck as a kind of program understanding tool here. So the way that we test operations that manipulate state like this is with a state machine model. Our test cases are going to be sequences of calls to the API. Duh, if you wanted to test the process registry, of course you're going to need to make a sequence of calls. But we also model the state of the registry. And we do that by defining a state transition function on the model for every operation. So we're going to know at each point in the state what the contents of the registry ought to be. And then we write postconditions that check that the API calls return correct results. And then when a test fails, one of the things that shrinking is going to do is it's going to figure out which of these API calls were not needed to provoke the failure, so that we just get a short test case that reveals what the problem is. OK, I'm going to model the registry state. How will I do that? I'm going to use a record with two fields, a list of PIDs and what I call a list of regs. So the PIDs is just going to record which processes I've spawned. I need that so I know what I can pass to register. And the second one just records which processes should be registered. It's a list of pairs of names and PIDs. OK, so my state transition functions in the model are going to add things to PID when I do a spawn, and add things to regs when I do a register, remove them when I do an unregister. So with this model, I can write a very simple specification of register. Here's what it looks like. We've got a precondition, first of all. So it's defined by a number of callback functions that characterize different aspects of register's behavior. The first one says, don't even try to call register unless you have some PIDs. Of course, you can't. The second one tells QuickCheck how to generate arguments for calls to register. It says, well, the arguments to register are a randomly generated name and one of the elements of the list of PIDs. And then we always define a wrapper function. So this says, how do I perform a register? Well, I call the Erlang register function, of course. In this case, the wrapper function is very trivial. Usually, there's something more interesting for a wrapper to do. And then finally, down here, I've got my state transition function, which says, how does the model state change when I register a name and a PID? And the answer is, we change the list of regs by adding to the end of the list a pair of the name and the PID. Now, I know you're looking at this code and you're thinking, hasn't he just re-implemented register? Isn't this just what register does anyway? So I thought I would show you the code of register. Well, not all of it, but here it is. This is what register does. And this, and this, and this, and this. So it's a BIF. It has to work in SMP with shared memory. It's tricky C code. Register is doing complicated stuff. The model is much, much simpler than the implementation. And that, again, is something that we usually find is the case. OK, so let's test it. So I've just built a really simple model that just basically says it's got the spec of register. It's got corresponding specs for spawn and unregister. Let's see what happens. Once again, I can't demo because of the network. But I can show you what would happen. So if I queue a build, now I've queued the first build. Not surprisingly, my tests fail. Otherwise, it wouldn't be much of a demo. So let's have a look. I've got one property, the registry property, which basically says that the implementation agrees with the model. And if we look at that, we can see that we found two different inconsistencies between the model and the code. Now, here, it's going to be more interesting to look at the output. There's a little plus sign there. I don't know if you can see it. If I click on the plus, then I can see what the QuickCheck output was for each of these tests. So let's do that. And the first one just calls unregister to unregister process A. And that raises an exception. Well, why does it raise an exception? Because I hadn't registered process A, of course. So I tried to unregister a name that was not registered. And you can't do that, or if you get an exception if you do. If we look at the other example, it's here. What this one does is it spawns a PID, and then it registers it twice with the name A. So two registrations with the same name, and the second call raises an exception. You're not allowed to register a name that is already registered. So let's fix these. I'll do the unregistered one first. Here's how I specified unregister. It says the arguments are just a random name, and the wrapper function just calls Erlang unregister. There's no precondition. Right? I shouldn't call unregister unless the name is in the registry. So what I need to add is a precondition function that says you can call unregister in a model state S if the name that you're going to unregister is a key member of that list of pairs in the model state. Okay, so I'm just saying, don't call unregister unless the name is in the registry. So if I add this function to my QuickCheck code and rerun the tests, then we come to here. Oh, the second build is also red. Of course, I haven't fixed the second bug. But if we open up the registry and go back to the examples, we can see that now that first example has turned green. Now, the output, I made the font a little bigger here. The output extends beyond the end of the slide. But what it says there is, OK, test case excluded by precondition. So I have saved the test case, and I'm still going to run it. But I'm checking that my precondition now says this is a bad test case. So in other words, it doesn't matter that it fails. You can also see that we've now got 3 examples here. So the second one we looked at before, but there's a third one that has appeared. Another problem. What is that? You can also see that there's a little caret sign beside it. What does that caret sign mean? Well, let's click on it. So if we do that, then that line expands into one example, which we'll look at in a moment, and a list of similar examples. So QuickCheck has found a number of failing tests, but it's classified them as similar. There's one that it shows us, and then there's others that you can look at if you really want to. What the examples say. Well, the first one spawns a PID, registers it with the name B, then calls unregister. That worked. And then it calls unregister again. And that raised an exception. Well, why? Because it's no longer in the registry, of course. But let's look at the similar examples. If we look at the second one, that's pretty similar, isn't it? Except that we use the name C instead of the name B. Can you guess what the third similar example is? We use D. I'm not quite sure what happened to A. We probably just haven't generated it yet. It'll turn up. So you can see that being shown all three of these examples, it would be too much information. But we're able to recognize the similarity and just show you one. So what's the problem here? Well, the problem is my precondition. Look, I wrote a precondition that says you can't call unregister unless the name is registered. So how come QuickCheck thought it was OK to run that test case where I called unregister twice? Well, the answer is I haven't told QuickCheck in the model that unregister actually removes the name from the registry. So I need to add a model state transition function for unregister as well. And if I do that and I rebuild my tests, now all of those additional tests pass. OK, so there's one remaining. And this one was the one where I registered the same name twice. And so if we look at the specification of register, I've only got one precondition here, and it says you can call register if you have some PIDs. But I need to add one that says you can only call register if the name is not already in the registry. So if I add that and rerun my tests, oh, look, the red test turned green. Did you see that? But another red test appeared. So I can see that I fixed the test case that I previously had, but now QuickCheck has found another test case that still fails. So my fix was not complete. And this is also something that we see quite often when we use QuickCheck. So if I look at this new failing test, this is what it does. It spawns a process, and then it registers the process twice with different names. Well, you know what? You're not allowed to register the same process twice, even with different names. I don't really understand why not. I mean, what's wrong with that? But at any rate, the built-in Erlang registry does not allow it. And so the precondition that I wrote wasn't strong enough. I just said the name must not be registered. I also need to say, and the PID must not be registered, which is just the second line. So if I add that and queue another build, now the build turns green. All my tests pass. So that's a simple example of testing using state machines. So these state machine models, they're a very convenient way to specify the behavior of stateful systems. And QuickCheck has a wide variety of different kinds of state machine models, because for most of the software that we test, state machines of one sort or another are what we need, and they're absolutely fundamental. We've seen QuickCheck-CI gathering a variety of interesting test cases all in one go and grouping them sensibly. I think this is really useful as well, so you're not overwhelmed by a morass of similar test cases. You just see the essentially different ones presented. Now, I know you're going to be thinking, what is all this reverse engineering of specifications? Right? That's not realistic. We're really looking for bugs in code. Of course, before you start testing, you know the specification of your code, don't you? If you'll believe that. You believe anything. Right, so what is the specification? Usually, it's just essentially code that has not been tested. Why on earth should it be right? And so in practice, we always find that there's a combination of reverse engineering what the specification should be. You know, documentation is A, never correct, and B, never complete. So there's always an aspect of that. And then the rest of the time, you usually find finding and correcting bugs in the code. Not for the process registry because it's so well tested, but in general, you find a mixture of these two things. So really what QuickCheck is doing is comparing two different descriptions of what the code should do, the implementation and the specification. And when you find an inconsistency, then you have to decide where the fault is. OK. I've shown you using QuickCheck and QuickCheck-CI on really tiny examples. And you might wonder, does this scale? So I want to just tell you a little bit about the largest QuickCheck project that we've done so far in recent years. And that was testing some AUTOSAR code for Volvo Cars. So we all know that cars contain a lot of software nowadays, 50 to 100 processors. And AUTOSAR is a standard architecture for that software. It specifies all kinds of stuff. But a part of it is the basic software, which you can think of as like the operating system that should run on these nodes. And this diagram shows what that operating system should contain. I should say there isn't just one implementation of AUTOSAR. There are lots of competing suppliers. And the car industry has agreed on a standard so that a manufacturer like Volvo Cars can combine components from different suppliers without worrying that they won't be able to talk to each other. That's the advantage of a standard, right? When things are standardized, you just put them together and things just work. Well, not always. And Volvo's experience was that basically, when you put the first car together to begin with, it never works. So that's why they paid us to develop acceptance tests for the basic software. So what does this stuff contain? Well, over on the right there is an Ethernet stack. That's something you recognize. So 4 of those things are protocol stacks. CAN, the second vertical column there, is the protocol stack for the CAN bus, a very commonly used network for communicating between processors and cars. LIN and FlexRay are other network protocols. The COM services on the top provide routing. The diagnostics, that's the thing that records the fault code. So when you take your car for a service, they say, aha, your third cylinder didn't fire 3 months ago, or whatever. So all of those white boxes are kind of components. What are the colored boxes inside? Those are the modules that make up those components. And AUTOSAR has a PDF describing what each of those modules should do. And just so you understand the scale of this, one colored box here will have a specification that is several hundred pages of PDF. So we took all this stuff, and we wrote we read 3,000 pages of AUTOSAR specifications, and we turned those into 20,000 lines of QuickCheck code. That's only about 6 lines of code per page. That's pretty good information density. We tested about 1 million lines of C code from 6 different suppliers, and we found more than 200 problems, of which more than 100 could be classified as problems in the standard. You know, you could have a requirement that said one thing and then a paragraph afterwards explaining it that said something different. So just because something is called a standard, it doesn't make it right. And there had been some attempts to develop test code for AUTOSAR previously. We were able to compare with one of those, and we found that our code was 10 times shorter and tests more. So we were very, very pleased with this. And if you want to ask, does this approach scale? Yes, it scales. The last thing I want to do is just show you 1 or 2 new ideas that came out of doing this project. So one thing that we all know, of course, is that when you have some code that you're testing, it's likely to have more than one bug in it. And the way that we have worked with QuickCheck in the past is we would run QuickCheck and we would find a bug. What do we do next? Well, fix the bug, of course. And then we'd use QuickCheck and find another bug, and then fix that one, and so on. And QuickCheck works very well in this manner if you're doing a kind of test-driven development. But before you fix the bug, there's a strong chance that every time you run QuickCheck, it'll show you the same bug. Right? If you think about it, we're testing randomly. However many bugs you've got, one bug is going to be most probable. And that's the one that QuickCheck will almost always find first. So that means that you really can't do any more until you fix that bug. It's good discipline. But when we were doing this Volvo project, we didn't even have the source code of the code we were testing. So this fixing it, this was done by the customer or one of the suppliers of the code. So that meant we had to report the bug to the customer. So what's this now? This is a test report. I can tell you, if you're supposed to send a test report to a customer, and they get it and they say, "What? You stopped testing after you found one bug?" They're not very impressed. So we had to do something about that. But I explained usually what we would do is fix the bug, and then QuickCheck will show us the next one. We couldn't do that. So what did we do? Unfix the spec, of course. We have spent a lot of time writing QuickCheck models for buggy implementations of AutoSAR so that we could go further and find the next bug. And as you can imagine, that is rather tedious work and a bit unsatisfying as well because, well, in a way, we're helping to diagnose the problem for the vendor because we're pinning down exactly what their code does wrong. But that wasn't what they were paying us for. So a new thing that we have come up with, we're just calling more bugs. And this is something that fits really nicely with the approach of QuickCheck-CI. What we do is when we find the first bug, then we generalize it, and we compute a bug signature from the bugs that we've already found. And then we can steer QuickCheck's generation so that we don't generate that bug anymore. This is really great because it means once we've found a few bugs, we know these parts don't work. Well, we don't waste testing effort trying to test those parts of the code anymore. We can focus testing on the areas that we don't yet know are buggy. And more bugs automates that completely. It's not in QuickCheck-CI yet, but it will be. And in practice, this was a really big win. So previously, we'd find one bug in one run of QuickCheck. Now we could leave it running overnight, and we'd come back, and there might be 20 bugs found in one go. Writing these test reports on each of these components, it could be a week's work. Now it's a few hours' work. That's ROI. So it's another of the fun things that we're able to do partly as a result of all of this. You want to try it out? You can take any GitHub project and register it with QuickCheck-CI, and we'll build it and run your properties. There is an example under Hans Svensson's GitHub account, which shows you what you have to do to make QuickCheck-CI run your code. And if you want to play, then I have an example of a very simple key value store. You can just clone that. Guess what? It's buggy. And you can experience what it's like to do QuickCheck-driven debugging. It's great fun. So that's it. QuickCheck in the cloud. Thank you.